and I will admit a new person entering. Okay, so welcome. Lecture 5 today, and it's about fluidization regimes, and there is much written in literature about fluidization regimes. And I'm afraid this lecture will give you more questions than answers, and more hypotheses than facts, actually. Because literature has been based quite much when it comes to fluidization regimes. It has been based on certain kind of fluidized bed units, and it is not necessarily describing what happens in boilers, in large-scale fluidized bed boilers. So we'll go into that. So maybe the main message I will convey here today is that what I'm going to show you is what is written in the books, what is written in literature, and I will also try to plant some criticism or some seeds of criticism that I hope grow in you, so that you are able to look at data or at what is written in the books with a bit of criticism, and trying to assess whether those findings are valid in your operation fields. And as I said, fluidized bed combustion, large-scale fluidized bed combustion, is a field which is not very much treated in literature, and it has its own characteristics which make it a little bit odd compared to others. And as we will see here today, it's not necessarily so that what is written about fluidization regimes applies entirely to fluidized bed combustion. So we'll go through this in the next hour. And let me start then by showing you the lecture index. And as you see here is first the mapping of fluidization regimes, the one that you could find from books, but I have modified it a bit to make some clarifications. Then we will go and see the main difference between FCC risers and CFB furnaces. These are the main two fluidized bed technologies, commercial fluidized bed technologies for reactors. So one is a catalytic cracking reactor, the other one is a combustion reactor, and we will see the differences. So much of this mapping of fluidization has been done for FCC risers, and as I said, very little is known about the fluidization itself, the solid flow pattern in CFB furnaces. And finally, we'll go and try to see what happens in large-scale CFB boilers. How does it look like there? And this will be a bridge for the next lecture. Okay, then let's start with the first point, and that is mapping of fluidization regimes. And maybe a good bridge is from the last lecture into this is this diagram that you should recognize by now. It's a bit of a fresh up here. So we have in the x-axis the Archimedes number that is somewhat telling us the size of the particles in a way. And in the y-axis we have the Reynolds numbers, which is in a way telling us a velocity. So these are dimensionless numbers. And what we saw is that by means of force balances or pressure balances, if you divide by an area, you can get you can derive theoretically the curves for minimum fluidization velocity and the curve for the particle terminal velocity. So we went through these derivations and reached these equations or these solutions for this force balance. And in the dimensionless form, they look like this then. To this, I commented that we could add the bed transport velocity, and this is a consequence of clustering. So what happens here is that the bed of very fine particles here in this end, in the low end of the x-axis, will not show any circulation even though our gas velocity exceeds the particle terminal velocity. That goes against any theory or this force balance over a particle. But the explanation for that is clustering, that very fine particles in these low Archimedes numbers, they tend to cluster a lot, and then they form larger solid clusters. They have a larger terminal velocity in practice then. And this means that you need to apply a higher gas velocity in order to start noticing some solid circulation in your unit. For the typical particles for CFB boilers, we should have Archimedes numbers above 1,000 or so. And then we are on the right half of the figure, and then you see that this effect is almost neglectable. While for other particles, finer particles, typical for fluid catalytic cracking, for example, it's called Gelder group A particles, this effect is noticeable. So we had these three curves then, and that's where we ended the last lecture. Here I'm providing you with some expressions for these three curves. There are others, but these are widely used, and there is three equations for each of these three curves. On top of that, we have also an equation telling us the transition of turbulent fluidization. And what is turbulent fluidization? Well, we have it here. If you remember, this is the x-axis, the fluidization velocity. The y-axis is the pressure. So in the beginning, we will have a fixed bed, non-fluidized, and the pressure will increase linearly, but also with some quadratic term. According to the Ergun equation, we looked at that. At some point, it will equal the weight of particles. This will be minimum fluidization, and then pressure fluctuations will start, but the mean, the average, will be kept constant at the weight of the particles. These fluctuations will increase with velocity, and at some point they will start decreasing again, and that's the transition to turbulent bed. So for a turbulent bed, they stabilize this pressure fluctuations, they stabilize at a relatively low value. Eventually, we reach the transport velocity, and then we enter what is called the circulating fluidized bed. So again, here you have the expressions for all these phenomena. Good. And then we come to what could be the holy script, so to say, of the fluidization regimes, or this is typically the diagram that everybody refers to when it comes to fluidization regimes. It's popularly known as the Grace diagram. It was John Grace at British Columbia University who published this, 86. And this is very much widely used, and it has replotted in many different ways. But the original one, if you go to the original paper, looks like this. So I stick to the original, and it may look a bit chaotic with a lot of notes and so in the beginning, but I will walk you through it. So what we have in the x-axis is the dimensionless particle size. And we went through this in the very first slides of lecture 3, if you remember. So this is the cubic root of the Archimedes number, and this is telling us the particle size in a dimensionless fashion then. Good. Then what we have in the y-axis is the dimensionless gas velocity, and that could be derived from the Reynolds particle number and the dimensionless particle size. And you have also that in some former slides. So it's velocity against size in a way. And then we have, when it comes to size, some divisions here. If you look, we have the Gelder groups. We also talked about that. So here on the left end, we have the C group. It's called here C group. These are cohesive particles like flour. It's not possible to fluidize these particles because they have very strong interparticle forces. Then come the group A particles. It's possible to fluidize this. Very nice. It's actually the easiest particles to fluidize. And these are typical for fluid catalytic cracking, for example, in petrochemical industry. A bit larger is the group B particles. These are typical then for fluidized bed combustion, gasification, chemical looping, and so on. And finally, we have group D particles. These are very large particles which are very hard to fluidize. They don't lead to any bubbles or so, but it's more about spouted beds. And we have the family of spouted beds. We have it here, and we also have moving fixed beds then, which are not fluidized. Okay, so if we remove the zones that are not fluidized beds in itself, or the solids A and D that do not, C and D that do not fluidize, then we get with the central part of the figure. And then we have group A particles and group B particles, and we have the division line in here. Good. And then what you see is these curves that I had shown you before. So here goes the curve for minimum fluidization. You have the equation, and we derived it through a force balance in red, the minimum fluidization. So below this line, we have a packed bed. You have it here, packed bed. Okay, then we have the particle terminal velocity here in blue, this force balance for a single particle. So in between these two, what we will have is a bubbling bed. So our bed will be fluidized, it will be bubbling, but it will not circulate. The circulation is given by the bed transport velocity, it's this green one. And again, this is what I was explaining in the former slide, that for very fine particles, you have a difference between the terminal velocity and the transport velocity of the bed because of clustering of these group A particles. But when you come to group B particles, typical for fluidized bed combustion also, we are typically in this region of the size. This effect, this difference is neglectable. So the bed transport velocity and the particle terminal velocity are very much alike. So as far as you keep in between this region, between these two, you have a bubbling bed. Then if you surpass this upper region, these upper curves, then you enter the field of circulating beds then. Finally, if you keep increasing velocity a lot, you will finally reach dilute conveying or pneumatic transport, as it is called, in which virtually any particle is a single particle and is not in contact with any other one, so to say. And that is not a fluidized bed itself, but it's something more like a transport reactor or a transport device. It doesn't need to be a reactor. So this links strongly to the three curves that we saw in the former lecture and in the former slide, but now seen on a wider perspective into a fluidization diagram. So again, this is a bit of the holy script for people working with fluidized beds. This was derived, as I said, or experimentally derived mainly from experience, and much of this experience was in units which are relatively small. So what I will show you now is modified from Grace and B 97. And this was, as I said, derived from narrow units, chemical CFB reactors with Gelder A solids. So I will walk you through a journey starting from very low velocities for these group A particles, and then just increasing velocity, gas velocity, but keeping the same size, Gelder A. So this is maybe a first note to do here, that what you typically read about fluidization regimes and the figures I will show you now, this is originated or derived from experience in these narrow reactors in group A particles. And we start with minimum fluidization. Before the velocity reaches minimum fluidization velocity, we have a packed bed, and that is not fluidization. So fluidization starts here with UMF. A first note to do is that I will, as I said, walk you through this journey going up in velocity. So we will go up in velocity, and the first significant velocity we meet is minimum fluidization velocity. But I have to notice one thing, and it is that typically in fluidized bed units, solids have a particle size distribution. It can be more or less wide, but it's not a single size. And all these expressions that we derived and so on, they are based on a particle size. You need one value for that. You cannot put a size distribution into those expressions. And we also discussed which is convenient mean particle size, representative mean particle size to use. It was this Sauter diameter, if you remember, which keeps the ratio of surface to volume constant. So remember, we will reach UMF based on this mean diameter, but this means that more or less 50% of the particles will be below this minimum fluidization and 50% will be above it. And there are interactions and so on. There are studies also showing that the presence of fines, so to say, decreases the minimum fluidization velocity. They act as a kind of lubricant for the coarser particles. So I just want you to be aware, these are velocities calculated for a mean. So when we reach the terminal velocity, for example, that is for the mean size, but it means that 50% of the solids almost, or more or less roughly, 50% will already be in conditions to circulate already. So this is something to keep in mind. Okay, if we increase velocity, we go from minimum fluidization. We are here in the diagram. We go from minimum, we go from this minimum fluidization into these. What happens with group A solids? Group A solids are particular in the sense that before the bubbling starts, you can increase velocity beyond minimum fluidization without having any bubbling. So the bed will expand, it will behave as a liquid, as a fluidized bed. It will have the properties of a fluidized bed, but you will not see any bubbles. And this is called delayed bubbling then. And this is called the minimum bubbling velocity here. Then you reach a minimum bubbling velocity in which you start actually seeing some bubbles. And this is what we see here. You enter this area of bubbling fluidized bed. You have bubbling here. So this is typical for group A solids, that before you see bubbles, you have minimum fluidization, you have a range of velocities in which the bed is fluidized, the bed expands, but it doesn't show any bubbling. Then you get this bubbling regime, minimum bubbling fluidization velocity. If you increase this for narrow reactors, one thing can happen, and it's that you reach slugs. This means that bubbles grow much and they can occupy, if not all, most of the cross section of the vessel. And this leads to slugging, and we discussed slugging shortly in the former lecture. And this happens when the aspect ratio of the bed is typically larger than 1. Okay, finally we get to some transition to the turbulent regime. We saw that in the former slide. The pressure fluctuations go down. We don't have these large bubbles anymore, but bubbles break down by themselves by the interaction with the solids. So the fluctuations of the pressure, they go down. Fluctuations of pressure are strongly related to bubble size. So still no circulation. Some solids are splashing here, but they fall back. But what we see is a breakup of the bubbles by themselves, and thus a decrease in pressure fluctuations. So this is called the turbulent regime. We are not circulating. We are in the upper part here, but still not circulating. So remember, circulation is somewhere around here, the transport velocity. It's not plotted in this diagram. Okay, and then when we reach the transport velocity, we enter a circulating fluidized bed. So we are here in this border now. This is the transport velocity. Then the lower border of this region tells us about the transport velocity. And what we have in fast fluidization with these narrow reactors and Geldert A group particles is that, well, we see solids lifting all the way up to the reactor, so we need to take care of this, and in order to keep the solids inventory, we need to recirculate them, otherwise they would just leave our system and the system would empty itself from solids. So first thing, we need to recirculate. Second thing, what we will see is a cluster formation. So the solids flow pattern here will be dominated by the presence of clusters. These particles will go together. That's a law of nature. They tend to go together to find the minimum resistance for the drag. It's like Yeah, like you have in birds flying, so to say, in the sky, or like you have professional cycling when people get after each other, or motorcycling in order to take profit of the wake from the one just in front of you. So they tend to group together and form clusters. They group together, they form these clusters, and in the end, these clusters are so heavy that by themselves they fall down again. So you have a lot of back mixing by clustering, by cluster formation here. So this happens when you are above the transport velocity initially for a region. If you keep increasing, then you will have a more dilute flow, and the particles will flow by themselves. So the concentration of the solids is so low here that the particles have a hard time finding each other and finding the wake of other particles. So the cluster formation is almost neglectable here. What you have indeed is still a back mixing. So all the solids lifting will not make it to the top because you have a back mixing at the walls. You see some formations of solids at the walls. So the solids go up and disperse laterally in a chaotic fashion, random walk. And if they hit the wall, they will typically then fall down through the wall to the bottom and restart their rise. If they are lucky, then they will get it to the top again and be externally recirculated through, again, a cyclone or some kind of solids recirculation device. And then we are up here then in conveying, pneumatic conveying, dilute conveying. So this is the typical picture, I would say, for Gelder A solids, and this is the one that you would find in any fluidization book, so to say. I just wanted to clarify a bit before we move on what characterizes each regime. So here we start having some bubbles. Next step, when you go over UK, this transition to turbulent regime, is that pressure fluctuations go down, and this is what you see here. You see UK, you have a transition here in which the pressure fluctuations go down, and then you enter the turbulent regime in which they keep constant with fluidization velocity at a relatively low level. So this is what you have here, turbulent regime. No circulation, but very moderate or decreased pressure fluctuations. And then here you have the transport regime, and here this diagram stops, but reality continues. And what we have is, again, in first place, some clustering, back mixing of solids dominated by clustering. They fall back because they cluster together. If you keep increasing, you have pneumatic conveying, no clustering, they fall back because they hit the wall. And there is a boundary layer for the gas in the wall, and they take profit of this low drag to fall back then. Okay, this is what you would find in, as I said, in any book. And now let's see how we can tackle the question, can we apply this knowledge to CFB boilers, to CFB furnaces? This is a question that we should ask ourselves. In first place, we should look at the characteristics of CFB furnaces and these FCC units then. Give me 5 seconds. Masen, I tend to lose my voice when lecturing after a few days, so hope it's not the case now. Okay, so we have the main 2 types of commercial fluidized bed reactors. There are other fluidized bed units, not reactors, which are commercial, but when it comes to reactors, these are, I would say, the ones with the highest revenues or the highest commercial markets. So on the left side, we have FCC, fluid catalytic cracking, and to the right side, we have solid fuel combustion. I was actually checking yesterday by curiosity about research papers on both, and they have been increasing much from the 80s, more or less, steadily, both. But fluid catalytic cracking is keeping the publication rate at about double as much as solid fuel combustion. And this is this can be done by or due to several reasons, but I believe one reason is that typically this is a process fluid catalytic cracking in which you need a lot of control, a lot of measurements, and then when you have a commercial unit, you have a lot of data in it that you can monitor, and then it's easy to do research. Unfortunately, for those of us working with combustion, typically you have very few measurements in the furnace. We will go through this later, but I mean, typically in the furnace you don't have any gas measurements. You measure gas after the furnace, so you don't have any clear picture of how combustion proceeds inside the furnace. There are, in the best of cases, 3 or 4 pressure taps along the furnace, and that's mostly it. So there is very little knowledge typically in terms of commercial units what happens inside here, because instrumentation is not needed to monitor combustion here inside the unit. While here you need a lot of monitoring to control the process, and then it comes for free, so to say, to use those data to learn more about the process and do research. Okay, so in fluid catalytic cracking, what we have is 2 reactors and some catalytic solids that need to circulate between the reactors. I will not go into the detail of cracking, but what we have are solids that need to circulate between these 2 reactors. And the way to force their circulation is to have this narrow riser here, in which you inject the gas, and then the solids coming down from this by gravity, they are pushed up by the gas here and enter the next reactor. So this is a riser, and this is, in this kind of units, is where all these typical regimes have been studied. So when it comes to industrial sized units, fluid catalytic cracking, the riser in fluid catalytic cracking units is the core of the studies when it comes to CFB research. In boilers, what we have is also a circulation here, but it looks very different. What we have is typically a very wide furnace. I had this simulation. We have a model here at Chalmers that we have developed with the boiler manufacturing industry. And this is a simulation we did for a 200 megawatt thermal megawatt unit. And this is quite a standard size. I mean, you have up to almost 600 megawatt. But for this, the dimensions are about 15 meters wide and about 5 or 6 meters in depth here. So cross section is about almost 100 square meters. And then you have, between 30 and 40 meter tall units. I have also drawn the unit at Chalmers here for comparison. So this is a mid-sized unit, and this is the smallest commercial CFB. It's the one here at Chalmers, 12 megawatt. The advantage with this CFB at Chalmers is that it was already at the design stage. It was designed with research purposes. So it's like a Gruyere cheese. You have a lot of holes in it, really a lot of holes to insert probes, gas probes, solid sampling probes. So it was from the design stage perforated along with all walls in order to be able to do research and to take a lot of samples and understand what happens inside. So here you have the sizes of this and how large is the riser of a fluid catalytic cracking. If we mark it in green here and we put it there, it's something like this. And here you have the first big question mark. Would all studies, all literature which is done from FCCs in this kind of units, is it relevant for what happens in these kind of units instead in boilers? And it's a question mark, and I'm not saying yes or not. I'm just putting a question, so to say. And I don't dare to answer. I would say the answer is that maybe some things are applicable or exportable between the 2 types of units. Maybe some things are not. I guess that's the most reasonable answer you could give. Let's try to dive a bit more into the differences between these 2 units. What has been observed is that for FCC units, you have a bottom bed. We were looking at bed expansion yesterday. So the bottom bed is the region which has a linear pressure drop, so to say, a constant pressure drop gradient. And this is only kept at low gas velocities for FCCs. As soon as you reach transport velocity, you don't have anymore a bottom bed here. Your solids concentration starts decreasing from the very beginning. While in CFB boilers, we see a bottom bed, we see a region at the bottom of half a meter or so that keeps a constant solid concentration. So this is a first fundamental difference between both. The second one is the size. Typically, the diameter of these risers is 30 to 50 centimeters, but you can see up to 1 meter. While for these furnaces, I gave you the dimensions before, about 100 square meters is not strange. So you can have something, yeah, around, so to say, 10 meters, which means that you will never reach slugging in these wide furnaces. They are so wide that the bubbles would never occupy the whole cross section. Another fundamental difference is the particles. You have much finer particles in FCC. Group A is another Gelder group, while here we have Group B. Differences between Group A and Group B. Well, Group A has this delayed bubbling. There is a how would you call that? There is a region in which in between minimum fluidization and minimum bubbling. So the bed is fluidized but doesn't show any bubbles. This does not exist here. Also, Group A, what we have in Group A is that the transport is delayed. It starts after the terminal velocity of particles, but for Group B, terminal velocity and transport velocity of the bed are the same. And finally, for Group A, you have a tendency of the particles to cluster a lot. For Group B, that tendency is much lower. So two kinds of solids. Also, the circulation rates, the solids concentration. You have solids flows of about 100 kilos per square meter per second in this riser. So very high solids density. While here it is about 10 times less, or even less, 10 to 100 times less, I would say. It can get down to 1 kilo per square meter and second in the top locations here. So you have also difference in solids concentration here. And finally, it relates to the particle suspension. So this is the gas porosity. So here you have 5% of particles in the upper locations. Here maybe you have 1% of particles volume. In terms of volume, 1% occupied by particles in the upper location. So there are fundamental differences between both kinds of units. And with this, I just want to illustrate again and make this question mark even bigger, so to say, are the learnings from FCCs relevant or exportable to large-scale combustors? And we will try to answer this now. And once more, I can't insist enough on this. Before answering, I just want to emphasize that the whole thing is a big question mark. So this is not really proven or accepted or established, what I will tell now, because it has not been investigated and there is a big lack of experimental data. And this is something that we are trying to tackle here at Chalmers in the next couple of years. I will tell you that in another lecture. We have a unit which we believe can help us much in investigating this kind of questions. Okay, so let's start then. Now, instead of rising here with velocity at a constant size with Group A particles, we will make the rise in velocity in the other region, in the region of Group B particles. And I will describe for you what we see. So first, now we're having Gelder B group particles. That is one characteristic for large-scale FB boilers. The other one is that the diameter, the equivalent diameter or hydraulic diameter of these vessels, of these risers, is much larger than the height of the bed. So we will not have slugging. So I have removed slugging from the former picture. I have also removed this delayed bubbling because it doesn't happen here. As soon as you reach fluidization, you will start have bubbling. And this is something that you typically notice when doing experimental work with group B particles. If you want to have minimum fluidization without any bubbling, it's very hard. It goes from a fixed bed, and it's very hard to have a minimum fluidization bed without any bubbles. Bubbles would show up at once almost. So if you simply touch the bed a bit from the side, you just knock on the wall a bit, bubbles will appear. So it's hard to get minimum fluidization without getting bubbles. So at once you will have some bubbles, some bubbling regime in this bed when you increase velocity. Okay, what's next step? If we have a bubbling bed and keep increasing velocity, what will happen? Well, the classical explanation, or what you find in books, is that you would reach this turbulent bed, this turbulent regime. And you remember what characterizes this is that the fluctuations, there is no circulation yet. Circulation starts here at the transport velocity. So there is no circulation, but the fluctuations, pressure fluctuations will go down at some point. Okay, let's try to see if this happens or not. As I said, data is very scarce on this because typically commercial units are not equipped with a lot of pressure taps, and you're not free to do experiments as you like in a 200 megawatt unit. But let's see if this happens again. Would this happen? Would fluctuations here at some point in a bubbling bed start to decrease again to enter this turbulent regime? Well, the data we have from the Chalmers boiler looks like this. And now let's have some patience here to explain this. You have the empty symbols. You have in the x-axis the fluidization velocity, so we are increasing velocity, and in the y-axis the standard deviation of the pressure, so pressure fluctuations. So the empty symbols, they show us that you I just wanted to show this blue line here. So we have the transport velocity somewhere here. So we reach the transport velocity, we reach this point, and we don't see any decrease in fluctuations. So that is a first suspicious fact that we see that is not according to this typical picture. Then we reach transport velocity, terminal velocity of the particles. We don't see any decrease in the fluctuations. Now let's follow the curve with the empty symbols. It starts here and it keeps increasing even after the circulation has started, and it never decreases even for the maximum fluidization velocity, 5.5 or so, or 5. We don't see a decrease. So if we are able to keep a dense bed in the bottom, we will see that the pressure fluctuations, they do not decrease. We don't see this decrease here. And we are far beyond this transport velocity. We are somewhere here. So this is a first observation. Second observation is that, yes, if we do experiments in another way, if we do experiments with a constant mass of solids without caring of the solids inventory, we have the same mass and we just increase velocity, then we would see that at some point the pressure decreases. But this is because we lose the bed. The bed is depleted. I was shortly telling you about this in the lecture yesterday, that as you increase velocity, more and more solids will populate the upper regions, and then you will deplete the dense bed. And in the end, you will have no dense bed. You will have no region with a constant solids concentration. And then, of course, you reach a decrease in fluctuations because your whole flow or your whole solids concentration is more dilute. So this is obvious. If you lose the bed, obviously you will see your pressure fluctuations going down. But I would say that the relevant case is this: when you keep a bed, you keep this dense region, but you don't see a decrease in pressure fluctuations. Thus, our conclusion here is that if you have a bottom bed, if you have enough solids to ensure that there is this bottom bed, we see that the pressure fluctuations keep increasing, and then this follows the definition of a bubbling bed. So we have a bubbling bed, or this definition of the bubbling bed even at very high velocities after transport circulation of the solids is established. So this means that the bottom part, at least, will keep according to this bubbling regime, and we don't see a transition to turbulent conditions. So that is a first observation that differs from what is written in the books, so to say. So we don't see this transition to a turbulent regime. We cannot observe this. And this is a long story. I could go into the details that we can observe that if we modified the bed geometrically and we put a lot of tubes inside and so on. But we don't have the time, unfortunately, for this discussion. But if you like to have it, then I will very much like to hold such a discussion with any of you. So conclusion, the bottom bed, we can increase velocity, but what we have seen is that for our maximum velocities that we have reached, we see still a bubbling regime, or the behavior of a bubbling regime here at the bottom with increasing pressure fluctuations. Now the question is, what happens here? The material, of course, ejects after this transport velocity is reached, so we will have material here. How will it behave? Well, and this is what we try to answer here. Again, just to re-walk you here, we have minimum fluidization, minimum bubbling conditions here. As we reach the transport velocity, we keep the bubbling characteristics here at the bottom, but we don't know what happens here. What will happen with the solids that have been ejected? If we recall the classical literature, they say that, well, solids, when transport is established, where solid circulation is established, solids can have two regimes. One in which the clustering dominates and the particles follow back by clustering and also by the walls, and the other one where there is no clustering and the solids back mixing is mainly by hitting the wall and then falling back again. So fast fluidization for the cluster dominated, pneumatic conveying if there is no clustering. So what do we have here in our large scale CFB boilers? Again, very scarce knowledge, but we can go and try to have a look at what is there. And these are measurements performed at Turów. This is a CFB boiler in one of the largest in the world, in Poland. And what we see here is an impact probe, it's called, a kind of a momentum probe. And then you can point it upwards or downwards and try to measure then how much hits of particles of solids you get on your probe, so to say. So here then we can see, we can start from the bottom here at about 4 meters above the bed distributor. And we see that there is quite much of the solid flow directed upwards, and then some are hitting downwards then. So there is these hitting downwards are clusters or solids flowing down, typically some kind of solid strands or solid groups, clusters. If we go a bit up at about 20 meters, so still we can see some hits upwards. These are the solids flowing upwards, much more dilute flow, less solids concentration, and some very few hits downwards. And the same is reproduced here at 36 meter high again. So what we see again is that it doesn't seem to be a very relevant cluster solids downflow, so to say. But if we take data from the Chalmers boiler, then we have the height of 6 meters or 5.5 here. Again, the particle flux upwards and downwards, and this is the wall. So here is the wall, and then we penetrate our probe here. So here in the central region, please disregard by now this first 20 centimeters by the wall. I will come back to that in the next lecture, but let's focus here on the center part of the unit. So this side effect here by the walls is this downflow, this local downflow of solids, but we will discuss that in the next lecture. So if we focus here on the central part of the solids flow here is where we want to see if there are clusters or not. At 5.6 meters, so relatively down at the low location of the furnace, what we see is that we have in dashed line, this is the upflow, and the solid line here, or almost solid line, this is the downflow of solids. This is the cluster. So here you have the net, the sum of both gives you the net flow. And as you see, the cluster is the difference between both here, and then the rest is solids going upwards. So yeah, apparently at this height there is some clusters, but not much compared to the whole flow. And again, noticing that if clusters form here and fall down, where you should gather them all, where you should see them all is here at the bottom, and this is what you're measuring here. So here you are seeing all the clusters that are falling down from upper locations, and still not much. So one conclusion from this is that there is very little solids back mixing via clustering then. And this leads us to the hypothesis. This is nothing more than an hypothesis that I want to throw up in the air, that we have a bubbling regime in the bottom bed, in the bottom region, constant solids concentration, but we don't see a decrease in pressure fluctuations, that we see pneumatic conveying or very little clustering here in the upper part by measurements. And we know by visual observation, and because it's measuring, we have seen that there are clusters in some region just above the dense bed. There are a couple or 3 meters in which clustering is dominant. So our hypothesis here is that apparently in CFB boilers, large-scale CFB boilers, you can find 3 different flow regimes in different regions, but the 3 of them sharing place, so to say, or sharing the same unit, but in different places. So we have, again, bubbling regime here in the bottom bed, fast fluidization in the splash zone, and then we see pneumatic conveying in the transport zone, or at least very little clustering then. So this is what we see from dedicated experiments. This is only one hypothesis, and of course it's the scientific method tells you to support them by facts. And if we look at the solids concentration profile of a large-scale CFB boiler, this is the Chalmers boiler. So if we look at it, sorry, it's not the yeah, it is, but at cold conditions. So if we look at that, what we would see is a first region with constant solids concentration, and this is the bottom bed. As I said, this is not something you would see in FCC units, but we see it even for high velocities in CFB boilers. So we see these, then we see another region with a certain solid concentration decay, and this is this splash zone. The solids concentration goes down rapidly. This means that intensive solids back mixing, solids decay, and this is the one that we presume has to do with intensive clustering or clusters that are ejected from the dense bed and just simply fall down ballistically. We will look more into this in the next lecture. And then we see another zone, a third zone with another back mixing rate. It's clearly differentiated from this intensive back mixing. Now the decay in solids occurs at a lower rate. And this is what we see here, the transport zone, where the solids back mixing does not happen by this fallback of clusters, but rather by particles, dispersed particles, single particles that hit the wall, join these wall layers of solids falling down. And this happens at another rate than the one we see here at the splice zone. So if you go and measure in a large scale boiler, you would see 3 regions. This is something we can see for all boilers that we have been studying now, or that are out in literature. It's about 10 of them, large scale, commercial scale, and all of them show, you could identify the same pattern. So again, one region here, constant solids concentration, another region, splash zone, strong solids back mixing, and then the uppest region occupying most of the furnace with moderate solids back mixing at a different rate than the one in the splash zone. So experiments tell you about 3 fluid dynamical regions clearly. And this is in line with the hypothesis I just showed for you, that we have 3 different regimes in our boilers. These typical solids concentration profiles is something that then we have been working with, and we have trying to characterize and to study more in detail. So the first region with a dense bed height, as we call it, constant solids concentration. Here you have it in logarithmic scale in the x-axis. So here you have it here. You can see bubbles or jets, gas formations, so to say. And then you have an intensive back mixing here by clustering or by ballistic throws. And this is the splash zone characterized by a certain exponential decay. And the decay constant is A, or we call it A. And above this splash zone, we have also an exponential decay. It looks linear, or it looks like a line in a log scale, but at a more moderate rate. So the decay coefficient, we call it K. And again, this is a pattern that is repeated for different measurement campaigns in different large-scale CFB boilers, and that agrees with the hypothesis that we showed here, or that I showed here before. So this will bridge, or this will link to the next lecture, this typical solids concentration profile. What happens in each of these regions? How does the solid flow look like in each of these regions? This is for this lecture. We have gone through the mapping of the fluidization regimes, the classical mapping you see from books. Then we have looked at the differences in commercial fluidized bed reactors between FCCs and large-scale CFB boilers, and then we have formulated some hypotheses and for large-scale CFB boilers, and seen that at least experiments seem to show that there are at least 3 different fluid dynamical regions in these units. More to come in the next lecture.